can be written as gamma I times the mole fraction. Okay, and we say the A can be considered as a real quantity over a reference state, right? And the gamma is equal to the real over ideal. Okay. Then we give you one example saying that if you have a two-component system with PA star equals to AT4 and the XA is equals to 0.25 and the PA you measure is 34, right? So then you know your A is equals to your real, which is 30, over your reference state, which is 80, right? So this is 0.375. That's your AI of your A. Okay, so it's AA. And your gamma A is equal to, the real is 30, ideal solution is 80 times 0.25. And this is 30 over 20. Then give you the gamma equals to 1.5. Okay, so this is what we went through this morning. Any questions? Okay, good. So now we need to discuss the.
Do we have a unit for the coefficient, the activity coefficient?
So do you have a unit for this? Okay, we said A is what? A is uniless, right? And the definition A is actually gamma times your xi. Does xi has any unit? No, right? So this is uniless, therefore this one is also uniless. Okay? So later on we will learn like anything inside a natural log. Okay, lake quantity will be always uniless. Okay. Sometimes you see I write this RT natural log PI, right? So what this means is actually this is not PI. This is PI over 1 bar. So the bar and bar cancels out. Okay, and if you write 1, it's equals you write nothing. Okay. So any quantities inside your natural log is uniless. Okay. All right. So with this concept in mind, then let's discuss. Okay. So how do you write your A for pure, solid, and liquid? Okay, so actually you know the term activity very long time ago, right? So when do you learn the term activity? Gen Chem 2 or Gen Chem 1? Gen Chem 2. You learn activity, right? So back to that time, you know the activity, sometimes people written in a way as concentration. Okay, and then back to that time, what is, when you learn this concept, what is the activity for pure solid and pure liquid? What's the A for pure solid and pure liquid? No one remembers? Okay, so when you learn the activity term, okay, typically it starts like this. Okay, you have a reaction A plus B equals to C. Then your equilibrium constant is equals to C to the C's power divided by A to the A's power, B to the B's power. Right? So what's this ABC? Typically with concentration. Right? Come on, this is Gen Chem 1. Okay, but in reality, actually you should not use concentration, you should use activity. Okay, so it's actually the activity of your A to the A's power divided by activity of B over B's power. Okay, and the numerator is activity of C to the C's power. That's the definition of your equilibrium constant. Okay, and the A, B, and C They can either be in solution or in the gas phase. They cannot be a pure liquid or pure solid. Okay, so when you have pure liquid, pure solid, those terms did not go into this equation. Back to that time. Okay, this just refresh your memory. Long time ago. Okay, so why? Yes, because we say the activity for the pure liquid, pure solid, A is equals to 1. Okay, so since it's 1, then no matter what power you have, it's just equals to 1. So effectively, with that in mind, even though you have pure liquid, pure solid, assuming A and B, they are just pure liquid, pure solid, they're just 1 to the A's power, 1 to the B's power. Okay? So, you know that A of pure liquid, pure solid, A equals to 1. Can you prove it? Okay, I guess at this stage you should be able to say yes. Okay, so if you have pure liquid, pure solid, you can write your mu equals to the mu naught times B times P minus P naught. Okay? So we also know you can write your mu as this, right? Mu is equal to mu naught, so this is plus RT natural log A